6.2 is still a skill they want us to walk through because the fact that some of the elements behind being able to use tables to do integrals is if you can develop some of those skills and some of your skills in integrating, using the other methods we've done before or being able to pick methods that we've used before becomes even sharper. So we're not going to focus much attention on this because, again, most of the time you're not going to be given a table in front of you for testing purposes. But it's a good skill to have because, a lot of times if you do mathematics, and even the math professors here, when they're doing their research and things like that, they're using other formulas that were established by other people and trying to take them another step further or use them to do something else. So, it isn't as though they have all these things memorized. If they do, it's usually because of constantly using it and, not necessarily because, they've committed everything to memory and they're perfectly at memorizing stuff either. Um, so integration by tables, still a good skill to kind of have you do some practice on. But it's not going to be one that's heavily tested. So, just again, take it for what it is, and that's the ability to be able to evaluate a circumstance and seeing what method would best suit it. So, many of the advanced techniques lead to integration formulas, which should be collected into a table. So, I mean, there are other integration techniques we haven't talked about. There are other techniques beyond integrating by parts. There's actually integrating using multiple variables. We're not going to get into that in this course. We're going to get into taking derivatives of multiple variables. So, we're going to kind of get, part of the way there, but, for the time being, we're not going to be worrying about, taking integrals of multiple variables as derivatives. So, other formulas may not be able to be made, by what you're going to be able to do, but there are other ways and other formulas that can stem from them. And those formulas that we're going to be making use of that were made through other methods are found on the back cover of your book, and I'm going to have a picture of that come up through this video to show you like how I'm checking it out and that sort of thing. So say for instance I want to find the integral of 1 over x squared minus 4 dx. Now, as I go through some of the methods that I have at my disposal, there's not much here. I mean, I have a dx. If I let u equal x squared minus 4, when I substitute, if I try to do a du, I'm going to end up with 2x dx. If I just have a constant, I could put that in. If I have a variable that's in there, that I have to substitute it, I'm not going to be able to do that. So, substitution looks like it's out. If I try to integrate by parts, it becomes, I have to do x squared minus 4 to the negative 1 power. Do I make that a u or dv? And, if I make it dv, that's part of the problem. I can't integrate it, so I can't make it dv. When I make it u, if I try to do a substitution with it, just to go through it really quickly, I just have to make sure to get my pen tool going. I'll use purple, right? If I let u equal x squared minus 4 to the negative 1 power and let dv simply equal dx, du is going to be negative 1 x squared minus 4 to the negative 2 power times 2x dx. V is going to equal x, and then when I do the integral uv minus v du, I'm going to get x over x squared minus 4 minus the integral. All this is going to multiply to the x, and that's going to, I have a negative on the dv, or on the du, so that's going to become a plus. I'm going to end up with 2x squared over x squared minus 4 squared dx. If I try to do a substitution again, now I have too much on top there. I don't, and if I try to do by parts again, if I try to let dv be anything but, the 2x squared dx, I'm not going to be able to do it. And if I let, u be the x squared minus 4 to the negative 2 power, I'm just going to end up with another integral that's even more complicated than this one that I have at the end of this. So I end up getting more and more integrals being built, as part of that process that I'm not going to be able to evaluate. So neither method works. So there is an advanced technique that would work that we're not going to cover. So what we would be relegated to doing is looking at the table. So let me get rid of all of this. So now, even though there's a table of integrals that you could use, I mean, some people just say, well, I'm just going to go to my, they have calculators that do integrals like this for you. And certainly that is an alternative as well. But then it's always going to simplify. It always regroups them weirdly. So, you end up not getting the answer. We end up getting an answer that we could tell that you didn't really look at the table or anything like that. So what we try to do here is we try to see how it fits one of the rules we have in that table that we have in the back cover. The denominator x squared minus 4 is of the form x squared minus a squared with a equaling 2. So we look at the table for integrals under forms involving x squared minus a squared and a squared minus x squared. And they do have formula number 15, which kind of fits into this category. And so basically all I would do is realizing that in this case here, as we do this problem, that a is going to equal 2, the rest of it becomes quite straightforward. All I have to do is really just put 2 in everywhere I see a, and I would have my formula. And that's all there would be to it, using the table. Sometimes it gets a little bit challenging to pick which one's going to work. So sometimes you have to do a substitution to transform a formula to fit a given integral formula. In such cases, both the x and the dx must be transformed. So, for instance, if you have this format here, okay, if you look very carefully, we do not have any x to the 4th powers in any of those general forms, okay? However, I can think of this as being x squared squared. I can think of this as being 1 squared. Now the whole idea behind that is if I let u equal x squared, then du has to be 2 times x dx, which, I have the x, I had the dx, I would need to get the 2 involved. So I could say, well, I'm going to let u equal x squared, du is going to equal 2x times dx, which means 1/2 of du is going to be x times dx. And so ultimately, and as we're going to see in the steps below, this is going to end up being 1/2 the integral of 1 times du over the square root of u squared plus 1, or 1 squared, if you want to think of it that way. And now it would fit one of the circumstances, one of the formulas we have there. So that's what they're going to show here. So, using this as my substitution, now this formula here, although it has u's, is fitting this formula here. So sometimes you have to be creative to make it fit. And so they're using, z instead of u for whatever reason. And then you have to substitute back in, since we let x be z squared, so when I get these other things into their right places, I don't know why they're doing it this way. It seems kind of awkward. Anyway. You could drop some of the absolute value bars at this point because when it's something that's positive, we know we could drop those. So that's the final expression for this answer. So Given a particular integral, how do we choose a formula? This is a very vague concept, so keep that in mind. Given a particular integral, how do you choose a formula? Well, find the formula that matches the most complicated part of the integral, making appropriate substitutions to change the formula into the given integral. So they kind of refer back to the example in there. But, again, it takes practice to do this, because what do they mean by the most complicated part? Well, what you might consider to be the most complicated part, someone else might consider to be something else, the other part of the integral to be the most complicated part. So, that's kind of a subjective description about how to make that choice. It's not really definitive. I mean, it's not going to be a steadfast rule. And, that sometimes is what causes students to have some difficulty. So that's where the practice element comes in. You have to practice to kind of get to know, like, okay, what do they consider to be the most complicated part? So let's walk through a couple. So we have this integral from 0 to 4 of 1 over the square root of x squared plus 9 dx. So the first question I'm going to pose to you, here is a copy of the table of integrals. Now, 1 through 8 are just basic formulas. 8 is the integration by parts formula. 1 through 5, 6, and 7 are the basic formats that we use for substitution. And of course, the first 6 are those we encountered early on in Chapter 5. We're just, the x to the n power rule, the e to the x power rule, that sort of thing. So, but these are the general rules that we have, okay? Which one of these rules am I going to have to use in order to, evaluate this integral? Well, as we look at this integral, I have the square root symbol, so, all these ones with radicals in the bottom seems to be a good fit there. I'm seeing an x squared, so there are some with x squareds in them. And it seems like it's fitting one in particular pretty closely. It seems to be fitting number 18 pretty closely. I mean, the only thing I have to make sure is that I put the appropriate plus or minus in. So if I have a plus, then I'm going to choose the pluses in this formula. If I have a minus sign between the x squared and my number, then that's it. Now the thing is, I have to keep in mind as I do this that what we're calling a, this is a squared, which means that a has to be 3. So as I do this, now I don't really have to know what a is, because the only time a is being used in here is it's still remaining squared. So that works out pretty easily. So if I use this rule to come up with my integral, let me erase the little thing I wrote before because it's kind of interfering with what I have up here. I'm just going to use that formula. I'm going to do the natural log of x, the absolute value of x plus the square root of x squared plus 9, evaluated from 0 to 4. I could really get rid of the absolute values now. Well, no, not really, because the x, I don't know, is positive until I look at the numbers I'm going to plug in for it. If I use 0 or 4, then what's inside the absolute value is going to be positive at the very least. I really don't need the absolute values. But when I put the 4 in, and I put the 0 in, I subtract, I end up with the natural log of 9 minus the natural log of 3. And if I use the rules that we've established for logarithms earlier in this term, then what I would get here is that's the same thing as the natural log of 9 divided by 3, which is the natural log 3. That's the exact answer. If you want to get a decimal answer at that point, that's fine, but oftentimes they're going to give the exact answer first. So, the next one, and the last one we're going to look over for this, as I said, it's not a skill we're going to focus a lot of attention on, but you do have some problems to practice. And I think pretty much the ones in web work really don't have you resort to the table, not very much. So I don't think there's any that you have to go use the table for in particular. So I think you're safe from even the web work problems on this. Find the following integral. So we have the integral of x minus 1 over x squared times x plus 1 dx. As I look at my options here, I see some formulas where I have an x in the numerator and junk on the denominator. I have instances where I have a 1 in the numerator and junk in the denominator. I don't really have any instances with the formulas that involve quotients where I have any kind of subtraction or anything like that occurring. So, as it's written right now, it's not going to fit any of these formulas. So, what do I have to do first in order to come up with a method using one of these formulas, or maybe more than one of these formulas, who knows, so I can actually start evaluating this integral? What is the first? What should these is what I should do first? Well, of the options that I've given you, the best option to go with is to separate this into a subtraction of two different integrals. I can separate this into the integral of x over x squared times x plus 1 dx minus the integral of 1 over x squared times x plus 1 dx. In the first integral, I can have a little bit of cancellation with my x and x squared. And so the first integral becomes the integral of 1 over x times x plus 1. And the next one still stays the integral of 1 over x squared times x plus 1 dx. With these now, which formulas are these going to be able to fit? And look very carefully, because some students overlook something that's kind of easy to handle, but they sometimes make the wrong choice based off of not seeing some of the nuances of this problem. So which formulas? There's going to be two separate ones, one for the first integral and one for the second integral. Which two formulas here am I going to be able to make use of? Well, again, the issue that sometimes students have in picking these out is because, there's some symbolism in the formulas I see over there that don't look like it's totally in these integrals I have over here. Let's look at these two integrals, and I'm going to rewrite them very slightly. The first integral, I can think of x as being the quantity 1x plus 0. Where 1 is a constant and 0 is a constant. I can think of the quantity x plus 1 as 1x plus 1. And the second quantity, the x plus 1 in parentheses, I can still think of as a 1x plus 1. The reason why I'm writing them this way is because if I write the first one this way and the second one that way, I can see where these a, b, c, d values are coming from. And as you see that, knowing that I'm going to let a be 1, b be 0, c be 1, and d be 1, the first one fits formula 10 really nicely. And the second one fits formula 12 very nicely if I consider a to be 1 and b to be 1. So that's what I mean by sometimes, taking a really good look at it, because, we have to keep in mind that certain like 1 as a coefficient is not usually typically written. A constant being added that's 0 is, again, typically not used. And the other thing you have to keep in mind is, even if you had a minus sign in these, you can think of it as plus a negative. So if I had an x minus 1 instead of the x plus 1s, I can think of d as being negative 1. It doesn't say that d has to be positive. So if you see deviations, what you're trying to do is make it fit as best as it can. So if I have to do that to, make myself, confident in my choice, if I have to write the coefficient of 1 in and put constants of zeros in and write subtractions as addition of negatives to show that it does fit a certain mold, then I'm certainly going to make use of that. So if I use these to my advantage, I can then come up with the integral. So what I would like you to do now is finish this integral with making use of these formulas and come up with your final answer. And when you do, see if it compares to one of these. Well, to finish this off, I'm just going to use the two formulas. So the first integral, when I put in the A, B, C's, and D's where they belong and everything else where it belongs, I end up with 1 over 1 times 1 minus 0 times 1 times the natural log of 1x plus 0 over 1x plus 1. When I use the formula 12 to do the second part, I end up with negative 1. And I have parentheses around places where I substituted. Unless it was with an expression, then I just kind of left it alone. So I'm going to have negative 1 over 1 times the quantity of 1 over x plus 1 over 1 natural log of x over 1x plus 1. That x by itself was in part of the formula, as you can see there. I forgot to write the other part of the parenthesis in there, but that's okay. And I put a plus c at the end because I know it's going to be an arbitrary constant because it's an indefinite integral. So now when I simplify a bit, I get the natural log, because 1 times 1 minus 0 times 1 is just 1, and 1 over 1 is 1. So this red part just becomes the natural log of x over x plus 1, minus this quantity becomes a negative 1 over x, minus the natural log of x over x plus 1. I then distribute the negative, and I get the natural log of x over x plus 1 over x plus natural log of the absolute value of x over x plus 1 plus c. I can see, excuse me, that I have this appearing twice. Those are the exact same terms, so I can add them together and combine them. And so I end up with 2 times the natural log of the absolute value of x over x plus 1 over x plus c. And that would be the final answer. That's all I have for this. It makes good practice in order to be able to, because even when you do integration by parts or by substitutions, sometimes you have to learn how to make it fit the situation you need it to. So this is a good skill where this can be practiced as well. So make sure you do the problems from the textbook in particular. That it's recommended to get a little more practice with this. As I said, it's not going to be heavily tested, but it still is a good skill to practice some of these other things that you do have to do. So that's all I have. If you have any further questions, please ask about them in class. But until I see you in class, I'll see you around. Have a good day, everybody.